How do scientists do it? How do they predict the future with such mind-boggling accuracy? Well, today, we're not just going to talk about it, we're actually going to build the very tools they use, right from scratch, with just a handful of numbers. Okay? Let's get into it.
I mean, seriously, think about it. How do we know the exact runway length a massive jet needs to land safely, or track an asteroid's path with enough precision that we can all sleep at night? It feels like magic, right? But it's not. It's physics. And the secret ingredient is something called a mathematical model.
And this is the secret sauce right here. A mathematical model isn't just some random jumble of letters and numbers. It's a bridge. It connects the stuff we can actually measure, like distance and time, to the stuff we want to predict. It's basically a recipe for seeing what happens next.
Okay, so predicting asteroids is maybe a little ambitious for today. So let's bring it back to the lab. Our big experiment? A simple toy car rolling down a ramp. Because it has a constant acceleration, it's the absolute perfect place for us to start our investigation.
Every great scientific quest starts with one thing: observation. So we let the car roll, and we get out our stopwatch and our ruler. We measure its position, its velocity, and the time. This data, this is our raw material. And hiding inside these numbers is everything we need.
And here it is, our treasure map. On the left, you've got time ticking away in seconds. In the middle, the car's position. And on the right, how fast it's going. Right now, yeah, it's just a list of numbers. But I promise you, by the end of this, we will have turned this raw data into 3 incredibly powerful tools for predicting the future. All right, mission number 1. We're going to build our very first tool. And to do that, we need to find the connection between the car's speed and time. If we can crack this little puzzle, we'll be able to predict its velocity at any moment in the future. So this is the fundamental question we have to answer first. Is there some kind of pattern here? As the seconds tick by, what's happening to the velocity? Just staring at the table doesn't really help much. We need a better way to see what's really going on.
And here's the secret weapon that every scientist has in their back pocket. You visualize your data. Plotting numbers on a graph can reveal these amazing hidden patterns that are just totally impossible to see in a table. So let's plot velocity versus time and see what we get.
And would you look at that? A perfect straight line. This is our aha moment. This is a huge clue. A straight line tells us there's a really simple, really predictable relationship happening. For every second that goes by, the velocity increases by the exact same amount. This is a pattern we can definitely work with.
Now, because we have a straight line, we can dust off an old friend from math class, the classic equation y equals mx plus b. All we have to do now is translate this from generic math speak into the actual physics of our rolling toy car.
So let's break it down. Our y-axis, that's just velocity. The x-axis, that's time. The b, where the line starts, well, that's just our starting velocity. But the slope, m, now that's the good stuff. The slope is the change in velocity divided by the change in time, which is literally the definition of acceleration. And boom, just like that, by swapping out the letters, we've built our first tool. See, this isn't just an equation anymore. It's a predictive machine. You give me any time you want, and this model can tell you the car's exact velocity at that instant. Okay, 1 tool down. That's huge. We can now predict the car's speed. But what about its position? Knowing where it's going to be is a real game changer. So it's time to forge our second tool. And we've hit a snack. When we plot the car's position against time, we don't get that nice, simple straight line. We get a curve. And curves, well, they're more complicated. It means we can't just use our simple line equation this time. We need a new plan of attack. But here's where we get clever. We can actually go back to our first beautiful straight line graph, because it turns out there's another secret hidden in there. The area under that line is exactly equal to the car's displacement, or, how far it's moved. To figure out that total area, we can just break up that weird shape into 2 simple pieces we totally know how to deal with: a basic rectangle on the bottom and a triangle on top. The rectangle's area is just its starting velocity times time. The triangle is 1/2 its base times its height. Then we just add them together. And when we put those pieces of the puzzle together, we get this, our second predictive tool. It might look a little scarier, but remember, we built it from simple shapes. And now, with this, we can predict the car's exact position at any moment in time.
All right, one more tool to go. This last one connects velocity and position directly, so you don't even need a stopwatch. And to build it, we're going to pull out a super cool technique from the physicist's playbook that they love for making hard problems easy.
It's called linearization. Now that sounds fancy, but the idea is actually really simple. Imagine you have a graph with a tricky, wiggly curve, but you have a pair of special math glasses that when you put them on, make that curve look like a perfect straight line. That's kind of what we're doing here. We're just changing what we plot to make the problem simple again.
So check this out. On the left, if you just plot velocity versus position, you get another one of those messy curves. But here's the magic. If instead of plotting velocity, you plot times velocity squared against position, bam, we get our beautiful, simple straight line back.
The trick worked. It totally worked. And you know what a straight line means by now, right? It means we get to pull out our trusty old friend, y equals mx plus b, for one last mission.
After we do the same kind of analysis on our new straight line graph, we get this, our third and final tool. This equation is amazing because it connects velocity and position directly. No stopwatch needed. It's an incredibly useful piece of our kit.
Okay, let's just pause for a second and appreciate what we've done. We started with literally nothing but a table of numbers from a toy car. We looked for patterns, we used a little geometry, we even pulled a clever math trick, and now we have a complete set of predictive tools.
And here they are, the whole shebang, these three equations. They're known as the kinematic equations. They are the absolute bedrock for describing motion, from a toy car rolling down a ramp to a planet orbiting a star. And the coolest part? We didn't just find them in a textbook, we built them ourselves, from the ground up. So this toolkit we've built is incredibly powerful if the acceleration is constant, but let's be real, the world isn't always that neat and tidy, right? You've got changing speeds, sudden stops, sharp turns. So what happens when acceleration itself starts to change? Well, that, my friends, is where physics gets really interesting.